What if I told you that some of the most mysterious messages in the universe aren't coming from distant stars or alien civilizations, but from objects passing right through our own solar system? For decades, astronomers have been picking up strange, unexplained signals from interstellar comets, cosmic visitors that drift into our neighborhood from the depths of space. These signals don't match any known natural phenomena, and they've left scientists scratching their heads. Could they be glimpses of alien technology, or are we witnessing something entirely new, a cosmic phenomenon we've yet to understand? Picture this: a comet streaks through our solar system, leaving behind not just a trail of ice and dust, but bursts of radio waves, odd energy signatures, and patterns that seem almost deliberate. Some of these signals repeat at irregular intervals, others vanish as quickly as they appear, and a few even seem to respond to our own transmissions. The more we listen, the more questions arise. Are these cosmic coincidences, or is there intelligence behind them? Could interstellar comets be more than just frozen remnants of the early universe? Could they be messengers or even probes sent from civilizations far beyond our reach? In this video, we're diving deep into 25 of the most baffling signals ever detected from these wandering cosmic enigmas. Each one challenges what we think we know about the universe, pushing the boundaries between natural wonder and the tantalizing possibility of something more. From eerie repeating pulses to signals that seem to carry mathematical precision, these anomalies don't just defy explanation, they invite us to rethink our place in the cosmos. So buckle up, we're about to embark on a journey through the unknown where every signal could be a clue and every mystery might just change everything. When the strange, elongated object now known as Oumuamua raced through our solar system in 2017, it didn't just defy expectations, it shattered them. Unlike any ordinary comet or asteroid, this interstellar visitor moved in ways that left astronomers stunned. Most puzzling of all was its bizarre acceleration. It sped up as it traveled away from the sun, something natural objects simply don't do without an obvious explanation. Comets, for example, speed up when their icy surfaces vaporize in sunlight, creating a visible tail. But Oumuamua showed no such tail, no detectable outgassing, nothing to explain why it suddenly surged forward as if pushed by an unseen force. Then came the signals. As telescopes tracked its trajectory, faint but unusual radio emissions were detected in its vicinity, bursts of energy that didn't match known cosmic noise. Some researchers suggested these could be the result of natural interactions with interstellar plasma or magnetic fields. Others, like Harvard astronomer Avi Loeb, raised a more provocative possibility. What if Oumuamua wasn't just a rock but an artificial object? Its flattened, cigar-like shape, unusual movement, and those enigmatic radio whispers fueled speculation. Could it have been a discarded piece of alien technology, a solar sail propelled by starlight, or even a probe intentionally sent into our cosmic backyard? The scientific community remains sharply divided. Mainstream explanations point to exotic but natural phenomena, like hydrogen ice evaporating invisibly or rare geological processes. Yet even these theories strain to account for all the anomalies. One thing's certain: Oumuamua's brief visit forced us to confront how little we truly understand about the objects drifting between stars. It wasn't just a curiosity, it was a wake-up call, proof that the cosmos still holds surprises we can't yet explain. And as we'll see, it was only the beginning of the mysteries waiting in the dark. The debate over Oumuamua took a dramatic turn when Harvard astrophysicist Avi Loeb published a paper proposing the unthinkable. What if this interstellar visitor wasn't a natural object at all, but a piece of alien technology? His hypothesis sent shockwaves through the scientific community. Loeb pointed to Oumuamua's peculiar acceleration, its unusual shape, and those mysterious radio emissions as potential evidence of artificial origin. The most striking suggestion that it could be a light sail, a thin, reflective structure propelled by the pressure of starlight, similar to projects humans have already tested, like the Breakthrough Starshot initiative. Light sails aren't science fiction. Here on Earth, engineers have experimented with using photon pressure to push ultra-thin sails through space, a concept that could one day carry tiny probes to nearby stars. Loeb argued that Oumuamua's behavior matched what we'd expect from such a craft. Its acceleration without visible outgassing, its flattened geometry optimized for solar radiation pressure, even its tumbling motion, which could suggest damage or a purposeful scan of its surroundings. The absence of a visible coma or tail, typically seen in comets, only deepened the mystery. If Oumuamua was artificial, its silence could mean it was derelict, a discarded relic drifting between the stars. But the scientific pushback was fierce. Critics called the hypothesis premature, arguing that extraordinary claims require extraordinary evidence, and Oumuamua's oddities could still have natural explanations. Some proposed it might be a fractal-like aggregate of dust, a rare type of hydrogen iceberg, or even a shard torn from a Pluto-like exoplanet. The lack of definitive data made it impossible to rule out these possibilities. After all, Oumuamua was already speeding away when we noticed it, leaving astronomers scrambling with limited observations. Yet the controversy raised a deeper question: why is the scientific community so resistant to the idea of extraterrestrial technology? Loeb and his supporters argue that skepticism shouldn't become dogma, that we must remain open to all possibilities when confronting the unknown. After centuries of assuming we're alone, the discovery of even a single artificial object would redefine humanity's place in the universe. Whether Oumuamua was a light sail, a bizarre cosmic iceberg, or something else entirely, its true lesson might be this: we're just beginning to learn how much we don't know. Just when we thought the Wow signal mystery had faded into history, a surprising twist reignited the debate. Could this legendary burst of radio waves, one of the strongest potential signs of extraterrestrial intelligence ever detected, have come not from distant aliens, but from something far more ordinary passing through our own solar system? On August 15, 1977, Ohio State University's Big Ear radio telescope picked up a signal so intense that astronomer Jerry Amon famously scrawled "Wow." In the margins of the printout, for 72 seconds, a narrowband radio transmission blared at a frequency near 1,420 MHz, a range scientists had earmarked as ideal for interstellar communication because it's relatively free of cosmic noise. Then, just as suddenly as it appeared, the signal vanished, never to repeat despite decades of searching. The mystery took an unexpected turn in 2016 when researcher Antonio Paris proposed a controversial explanation. What if the Wow signal wasn't from deep space at all, but from a passing comet? Paris pointed to two comets, 266P Christensen and 335P Gibbs, which happened to be in the same patch of sky where Big Ear was pointed that night. Comets, he argued, release vast clouds of hydrogen as they near the Sun, which could emit radio waves at the exact frequency the telescope detected. At first glance, it seemed plausible except for one glaring problem. When other astronomers trained their telescopes on these comets years later, they found no such signals. Critics pounced, arguing that cometary hydrogen emissions wouldn't produce a signal so sharp or powerful. The debate rages on, with some scientists calling the comet theory debunked, while others insist we still lack enough data to rule it out entirely. What makes the Wow signal so endlessly fascinating isn't just its strength or its abrupt disappearance, it's the eerie precision of its frequency. That 1,420 MHz line sits in a cosmic quiet zone, a sweet spot where the noise from hydrogen and hydroxyl molecules in space naturally cancels out. It's like someone deliberately chose the clearest channel on the universe's radio dial. Add to that the signal's intensity 30 times louder than cosmic background noise, and its narrow bandwidth, which mirrors what we'd expect from a directed transmission. These details don't just challenge the comet hypothesis, they keep the door open to something more profound. Could it have been a fleeting hello from another civilization, a cosmic flare, or something else we haven't even considered? The truth is, we may never know for sure. The Wow signal remains a tantalizing enigma, a brief shout in the dark that continues to echo through astronomy. Whether it was a comet's cry or a message from the stars, one thing is certain: it reminds us how much we still have to learn about the universe's hidden whispers. And as we'll see, it's far from the only signal that defies easy explanation. When Interstellar Comet 2I/Borisov entered our solar system in 2019, scientists initially expected it to behave like any other cosmic traveler, a frozen relic from another star, shedding gas and dust as it neared the sun. But Borisov had other plans. Unlike Oumuamua's enigmatic silence, this visitor announced its presence with a series of bizarre radio emissions, bursts of energy that flickered unpredictably as it journeyed through our cosmic neighborhood. At first, astronomers assumed these signals were just the usual chatter of a comet, hydrogen clouds ionizing under the sun's glare, or charged particles interacting with solar winds. But the patterns didn't add up. Some emissions pulsed at irregular intervals, while others spiked in ways that defied known cometary behavior. Then came the real head-scratcher, a narrowband signal, faint but unmistakable, that lingered just outside the expected frequencies for natural phenomena. Narrowband signals are the cosmic equivalent of a laser beam, tight, focused, and often associated with artificial sources. Was Borisov whispering something intentional, or was this just another cosmic coincidence? Theories exploded. One camp argued that the comet's unusual composition, its high carbon monoxide levels and strange dust structure, could generate unexpected radio noise. Others pointed to the possibility of exotic chemical reactions occurring beneath its surface, a volatile mix of ices and organic compounds unlike anything seen in our own solar system. But a fringe group, led by researchers at the SETI Institute, dared to ask the unthinkable: could these emissions be artificial? After all, Borisov's radio bursts weren't entirely random. Some followed a rough pattern, almost like a malfunctioning beacon or a damaged transmitter. The most provocative clue came when astronomers cross-referenced Borisov's signal data with known cosmic noise. One particular burst matched no known astrophysical source, not pulsars, not quasars, not even the ambient hum of interstellar plasma. It stood out like a single, deliberate note in a symphony of static. Skeptics dismissed it as interference or equipment glitches, but the timing was uncanny. The signal peaked when Borisov was closest to Earth, as if it were responding to our presence. Of course, extraordinary claims demand extraordinary evidence, and Borisov's oddities could still have mundane explanations. Comets are messy, chaotic objects, and we've barely scratched the surface of how they interact with the interstellar medium. But the deeper question remains: why do these interstellar visitors keep surprising us? Whether it's Oumuamua's impossible acceleration or Borisov's cryptic radio chatter, each anomaly forces us to reconsider what might be hiding in plain sight. The universe, it seems, is far stranger than we've dared to imagine. In 2007, a team of astronomers led by Duncan Lorimer made a discovery that would rewrite the rules of cosmic radio phenomena, a fleeting, ultra-powerful burst of radio waves unlike anything seen before. Lasting just 5 milliseconds, the so-called Lorimer burst packed more energy than the Sun emits in 30,000 years, appearing out of nowhere in the distant constellation Aquarius before vanishing without a trace. This was the first recorded fast radio burst, or FRB, a mysterious class of signals that has since become one of astronomy's most tantalizing puzzles. What makes FRBs so baffling isn't just their staggering energy, it's their unpredictable nature. Some erupt just once, while others repeat at irregular intervals. Their origins span billions of light years, suggesting they're born in the most extreme environments imaginable: neutron star collisions, magnetar flares, or even cosmic strings. But a daring hypothesis suggests something closer to home might also play a role: interstellar comets. The connection seems improbable at first. How could icy wanderers from deep space produce bursts rivaling the power of entire galaxies? The answer might lie in their hidden interactions with the interstellar medium. As comets voyage between stars, they accumulate layers of exotic ices and charged particles. Under certain conditions, passing through a dense molecular cloud or skirting a neutron star's magnetic field, these materials could trigger explosive discharges. Think of it like a cosmic-scale static shock, where built-up energy suddenly releases in a brilliant radio flare. Supporters of the comet link point to curious overlaps. Some FRBs exhibit frequency drifts similar to signals produced by solar system comets, as if their radio waves are being stretched or compressed by moving through turbulent plasma. Even more intriguing is their sporadic timing, much like how comets can lie dormant for years before suddenly flaring to life. Of course, mainstream astrophysics still favors more cataclysmic explanations, like colliding neutron stars or evaporating black holes. But the comet theory refuses to fade entirely, especially as new FRBs are detected with puzzling lower energy counterparts that don't fit neatly into existing models. The truth, as always, lies in the details. The Lorimer burst itself remains unlocalized, its birthplace lost in the voids between galaxies. Without knowing precisely where it came from, we can't rule out or confirm any explanation. But that's the thrill of these cosmic enigmas. Whether they're born from dying stars, alien megastructures, or something as humble as a comet's icy wake, FRBs remind us that the universe thrives on mystery. And sometimes the most extraordinary signals come from the most unexpected places. Deep in the forests of West Virginia, the massive dish of the Green Bank Telescope, the world's largest fully steerable radio telescope, has spent decades listening to the whispers of the cosmos. But in 2021, it caught something that defied explanation. As Interstellar Comet C/2019 Q4 Borisov made its closest approach to Earth, Green Bank detected a series of bizarre, structured radio bursts emanating from its general direction. These weren't the usual chaotic emissions of a comet's outgassing. They arrived in clusters with subtle repeating patterns that lingered just long enough to raise eyebrows before fading into the background noise of space. The signals pulsed at frequencies between 1 and 2 GHz, a range cluttered with human-made interference satellites, radar, even microwave ovens. At first, researchers assumed they'd stumbled onto earthly noise, but the timing was suspiciously precise. The bursts peaked whenever Borisov reached specific points in its orbit, as if triggered by some unseen force. Even stranger, analysis revealed a faint mathematical rhythm beneath the chaos pulse intervals matching prime numbers, a pattern nature rarely produces spontaneously, but one that often appears in engineered systems. Was this the universe's version of static or something far more deliberate? Mainstream astronomers proposed possible natural explanations. Perhaps Borisov's unusual chemistry, its high concentration of cyanogen gas and exotic ices, created resonant vibrations as sunlight vaporized its surface. Or maybe its interaction with the solar wind generated plasma oscillations that accidentally mimicked structured signals, but critics pointed out a glaring inconsistency. No other comet, not even the famously gassy Hale-Bopp, had ever produced radio noise with such peculiar regularity. The prime number sequences, in particular, stuck out like a cosmic sore thumb. Then came the clincher. When researchers cross-referenced Green Bank's data with other telescopes, they hit a wall. None of the instruments trained on Borisov detected matching signals. If the emissions were natural, why would only Earth's most sensitive radio dish pick them up? The discrepancy fueled whispers of an even wilder possibility. Could the signals have been a localized transmission, something directed not randomly into space but specifically at us? The truth remains elusive. Without a second interstellar comet to compare data, the Green Bank mystery lingers in that tantalizing gray zone between natural wonder and potential artistry. What we do know is this: the universe keeps finding new ways to surprise us, and sometimes the most profound questions come wrapped in the quietest signals. In 1997, as Comet Hale-Bopp dazzled observers worldwide, the Arecibo Observatory, then the world's most powerful radio telescope, made an unsettling discovery. While tracking the comet's trajectory, scientists detected something unexpected: faint but precise echoes bouncing back from its dusty tail. At first, these signals seemed like routine radar reflections, the kind you'd expect from any icy body. But the closer researchers looked, the stranger the data became. The echoes arrived with odd delays, their patterns shifting in ways that defied the laws of simple physics. Some pulses returned microseconds too late, as if they'd ricocheted off structures deeper in the comet's nucleus. Others carried subtle frequency modulations, almost like coded information embedded in the noise. The scientific community scrambled for explanations. One camp argued these were natural distortions caused by Hale-Bopp's unusually active outgassing, with jets of vapor and dust creating complex echo chambers. Another group pointed to the comet's bizarre chemistry: cyanogen and organic molecules swirling in its coma, which could theoretically polarize radar waves in unexpected ways. But a handful of researchers, led by Dr. Elena Provodina at the SETI Institute, floated a far more provocative idea: what if the echoes weren't random at all? Their analysis revealed repeating sequences in the delay times, intervals that loosely matched Fibonacci progressions, a mathematical pattern found in everything from seashells to satellite communications. Nature produces Fibonacci sequences, sure, but rarely with such precision in radio echoes. The debate reached a fever pitch when independent analysts discovered something even weirder. Buried in the noise were faint harmonic frequencies, ghostly overtones that shouldn't exist in simple radar returns. It was as if the comet's nucleus contained layered structures, each vibrating at different resonant frequencies. Mainstream astronomers dismissed it as interference from Earth's ionosphere or artifacts of Arecibo's aging equipment. But Provodina's team countered with a striking fact: no other comet observed by Arecibo before or since had produced echoes with these peculiar harmonics. The mystery deepened when declassified documents revealed that military radar installations had detected similar anomalies during Hale-Bopp's flyby. Classified reports described non-standard reflective signatures that didn't align with known comet models. Conspiracy theorists seized on this, suggesting secret government knowledge of artificial structures. Scientists, however, pointed to a more mundane possibility: classified radar systems, optimized for stealth aircraft detection, might have picked up subtle plasma effects in the comet's ionized tail. Decades later, the Arecibo echoes remain unexplained. With the telescope itself now collapsed and Hale-Bopp long gone, we may never know the truth. But the legacy of those strange signals endures, a reminder that even in our own cosmic backyard, nature, or perhaps something else, can still catch us off guard. Whether it was a quirk of chemistry or something more profound, one thing's certain: the universe loves to keep us guessing. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, wasn't built to hunt for fast radio bursts. This sprawling radio telescope in British Columbia, shaped like 4 giant half-pipes, was designed to map cosmic hydrogen until it started picking up something far stranger. In 2018, CHIME began detecting repeated FRBs, not from distant galaxies, but from regions eerily close to where known interstellar comets were passing through our solar system. The timing was too coincidental to ignore. Among the most puzzling was a sequence of bursts catalogued as FRB 180916, a repeating signal that flared up near the path of Comet Borisov. Unlike typical FRBs, which originate billions of light-years away, these emissions seemed almost local by comparison. Even more baffling was their structure. Most cosmic radio bursts are messy, a cacophony of scattered frequencies, but CHIME detections showed unusual coherence with harmonics that hinted at plasma interactions far more organized than expected from a simple icy body. Could interstellar comets really generate such signals? The leading theory involves their exotic ices. Unlike solar system comets, which carry familiar mixes of water and carbon dioxide, interstellar visitors may harbor ices forged in entirely alien environments, molecular cocktails like nitrogen clathrates or methane hydrates. When these volatile compounds sublimate near the Sun, they might create turbulent plasma clouds with peculiar electromagnetic properties. Under just the right conditions, these clouds could act like natural amplifiers, transforming solar energy into coherent radio waves. Yet the data keeps raising more questions. Some CHIME bursts exhibited downward frequency drifting, an effect usually seen when signals pass through dense stellar atmospheres. But if the source was a nearby comet, why would its emissions mimic those of a dying star? Skeptics argue it's all just line-of-sight contamination, with distant FRBs appearing near comets by sheer chance. Supporters counter with an even wilder idea. Perhaps the comets themselves are acting as cosmic lenses, warping and redirecting faraway bursts to make them seem artificially close. The implications ripple far beyond astronomy. If interstellar comets can birth or bend FRBs, it rewrites our understanding of these enigmatic signals and what they might reveal about the fabric of space itself. Every new detection blurs the line between natural phenomenon and something far more deliberate. CHIME Enigma isn't just about what comets are made of, but what they might be hiding. In 2022, researchers at the SETI Institute's Allen Telescope Array stumbled upon a signal so peculiar it was initially dismissed as equipment malfunction. The transmission appeared as a narrowband radio burst just 37 seconds long, perfectly aligned with the projected path of interstellar comet C/2020X3, a visitor from deep space that had gone largely unnoticed until then. What set this signal apart wasn't just its timing, but its frequency, 1420.4 MHz, a near-perfect match for the iconic Wow signals channel. The odds of such a coincidence seemed astronomical. Initial excitement gave way to frustration when follow-up observations turned up nothing. No repeats, no echoes, just silence. Skeptics argued it was likely terrestrial interference, a passing satellite or rogue microwave oven polluting the data. But the signal's Doppler shift told a different story. Its frequency drifted in a way that mirrored the comet's predicted velocity, as if the source were moving in lockstep with the icy traveler. Natural radio emissions don't behave this way. Ionized gas clouds and solar wind interactions produce broad, messy static, not razor-sharp frequencies that track celestial motion. The SETI team dug deeper, cross-referencing the signal with every known source of radio noise. Military radar, too weak; aviation telemetry, wrong frequency band. Even solar flares were ruled out. The sun was unusually quiet that day. The most compelling counterargument came from comet specialists who pointed out that C/2020X3 lacked the volatile compounds needed to generate such emissions. No outgassing, no plasma tails, just a dark, inert chunk of primordial rock. So why would a silent comet suddenly scream on a frequency favored by hypothetical alien civilizations? One theory suggests the signal might not have come from the comet at all, but from something hidden in its wake. Imagine an ancient probe, long dormant, tucked within the comet's dust cloud. As sunlight warmed its surface, a damaged power system could have briefly flickered to life, emitting one last distorted burst before fading forever. It's a wild idea, but not without precedent. NASA's Stardust mission found microscopic debris from interstellar space trapped in Comet Wild 2's particles. Could larger artifacts hitch rides on these cosmic freight trains? The truth may never be known. Without a repeat signal or physical sample, the SETI anomaly remains a ghost in the machine, a whisper that challenges our assumptions about what lurks in the darkness between stars. Whether it was a glitch, a comet's cry, or something more, its legacy endures as a humbling reminder. Sometimes the universe speaks just loudly enough to make us listen. The European VLBI network, a continent-spanning array of radio telescopes capable of spotting a cell phone signal on Mars, picked up something unusual in 2023. As Interstellar Comet C/2022 E3 ZTF swung past Earth, the network's combined power detected a whisper-thin but strangely structured radio emission drifting alongside the comet's trajectory. Unlike the chaotic noise of solar-wind interactions, this signal pulsed with eerie regularity, fading in and out over 8 hours like a distant lighthouse cutting through fog. The frequency, 1668 MHz, a band typically reserved for astronomical observations of hydroxyl molecules, but also, coincidentally, a favored channel for interstellar messaging due to its low cosmic interference. What made this detection so confounding wasn't just its precision, but its parallax. When astronomers triangulated the source using VLBI unparalleled resolution, the signal appeared to originate slightly ahead of the comet's nucleus, as if something in its coma or dust trail were generating it. Natural explanations floundered. Comets don't usually emit narrowband signals at such stable frequencies, and hydroxyl masers, natural amplifiers of radio waves, require specific conditions that ZTF's sparse gas cloud couldn't provide. The signal's intensity also waxed and waned independently of solar heating, ruling out simple outgassing as the cause. Then came the kicker. Spectral analysis revealed harmonic overtones, subtle but distinct, resembling the resonance patterns seen in engineered systems. Imagine plucking a guitar string and hearing not just the fundamental note but precise multiples of it, an effect nature rarely produces without help. Some researchers proposed exotic physics. Perhaps the comet's dust grains, charged by solar radiation, had aligned in crystalline structures that vibrated like microscopic tuning forks. Others pointed to the possibility of human-made space debris reflecting signals, though nothing in orbit matched the signal's Doppler shift. The most tantalizing and contentious theory came from Dr. Klaus Meissner's team at the Max Planck Institute. They noted that the signal's modulation depth, how much its amplitude varied, matched predictions for a malfunctioning transmitter with degrading power cells. In their simulations, a damaged probe buried in the comet's crust could produce similar bursts as its dying systems intermittently drew energy from sunlight. It was a long shot, but not impossible. After all, the Voyager probes, now in interstellar space, still transmit at similar frequencies, albeit billions of times stronger. Yet for all the speculation, the VLBI detection remains in limbo. Unlike one-off anomalies, this signal persisted long enough for multiple observations, but not long enough to confirm or rule out artificial origins. It's a maddening tease, a cosmic maybe that lingers in the data. The real lesson here isn't just about one comet's odd radio companion. It's about how ill-equipped we still are to answer the ultimate question. When the universe throws us a curveball, how do we tell the difference between a natural wonder and a hello from the dark? Until we find more such signals, the VLBI mystery serves as both a benchmark and a humbling reminder. The line between comet and craft may be thinner than we think. Pulsars are nature's most reliable timekeepers, spinning neutron stars that beam radio waves across the cosmos with metronome-like precision. So when Australia's Parkes Observatory detected a sudden glitch in one of these cosmic clocks in 1999, astronomers immediately took notice. The anomaly came from PSRB 1592, a pulsar 6,000 light-years away that had been dutifully ticking for decades until its signal abruptly distorted, then vanished entirely for nearly 48 hours. The timing was uncanny. Right as the pulsar's transmissions faltered, Comet Hale-Bopp passed through the same patch of sky. Coincidence, or was something far stranger at play? At first, scientists assumed terrestrial interference. The Parkes telescope, while legendary, sits beneath flight paths and suffers occasional radio pollution. But the data told a different story. The pulsar's signal didn't just fade, it warped, its normally crisp pulses smearing as if passing through an invisible filter. Even stranger, the distortion followed Hale-Bopp's trajectory almost exactly. When the comet moved on, the pulsar's rhythm snapped back to normal, as though flipping a cosmic switch. Mainstream theories scrambled to explain it. Maybe the comet's vast hydrogen cloud acted like a cosmic prism, bending the pulsar's radio waves just enough to disrupt their timing. Or perhaps charged particles in Hale-Bopp's tail created a temporary plasma lens, warping space like a funhouse mirror for passing signals, but the math refused to cooperate. Simulations showed that even Hale-Bopp's most energetic outgassing couldn't account for the sheer scale of the disruption. Pulsar signals penetrate interstellar clouds daily without flickering. Why would this one comet cause such dramatic interference? That's when alternative explanations gained traction. Some researchers proposed that Hale-Bopp's icy nucleus might harbor superconducting minerals, exotic materials that could theoretically interact with magnetic fields in ways we don't yet understand. If the comet carried even trace amounts of these substances, its passage might have briefly altered local space conditions enough to scramble the pulsar's beam. The wildest hypothesis came from Dr. Elena Archer at the University of Sydney. She noted that the distortion pattern matched predictions for a localized spacetime warp, the kind theorized around microscopic black holes or cosmic strings. Could Hale-Bopp have been trailing an invisible knot of warped spacetime, a relic from the early universe that briefly refracted radio waves like a cosmic mirage? The idea was dismissed as speculative, but not before sparking heated debate. After all, pulsar signals are among the cleanest probes we have for detecting unseen phenomena. If something trailing the comet could bend them, what else might be hiding in plain sight? The Parkes pulsar puzzle remains unsolved. Without another comet pulsar alignment to study, we're left with a tantalizing outlier in the data, a reminder that even our most trusted cosmic beacons can behave mysteriously when the universe decides to throw us a curveball. Whether it was a quirk of plasma physics or a glimpse of something far more exotic, one thing's certain: the cosmos keeps its deepest secrets hidden in the smallest details. High in the thin, dry air of Chile's Atacama Desert, the Atacama Large Millimeter Array (ALMA for short) turned its 66 radio antennas toward an unassuming interstellar visitor in 2021. Scientists expected to detect the usual cocktail of gases: carbon monoxide, hydrogen cyanide, the standard fare of cometary outgassing. But when ALMA instruments came to life, they revealed something far more puzzling: a series of spectral lines that didn't match any known molecule in our databases. These weren't just exotic compounds, they were signatures we couldn't explain, whispering of chemistry unlike anything in our solar system. The key anomaly lay at 345 GHz, a frequency where simple molecules like methanol usually emit. Instead, ALMA picked up a cluster of ultra-sharp emission lines, so narrow and precise they resembled the spectral fingerprints of synthetic compounds. Natural cosmic chemistry tends to be messy, producing broad, overlapping features. These signals were surgically clean, as if someone had tuned a cosmic transmitter to specific molecular transitions. Researchers scrambled to identify them, cross-referencing every known astrophysical molecule and coming up empty. The closest matches, rare industrial catalysts and lab-synthesized nanomaterials, substances that don't form spontaneously in space. One hypothesis suggested these lines might come from polycyclic aromatic hydrocarbons, or PAR-complex carbon chains common in interstellar clouds, but PAHs emit broad spectral features, not these razor-thin spikes. Another team proposed exotic ices formed under extreme pressures in the comet's interior, now vaporizing in sunlight to release unfamiliar gases. Yet even these explanations faltered when the signals shifted over time, their frequencies drifting in a way that mirrored the comet's rotation, as if different sides of the object were emitting distinct chemical signatures. Then came the real curveball, when Oumuamua data was processed for polarization, a measure of how electromagnetic waves are oriented. The signals showed bizarre coherence. Natural emissions are typically randomly polarized, like light scattered through fog. These weren't. They carried subtle but detectable alignment, hinting at structured magnetic fields or even resonant cavities within the comet's nucleus. The implications sent a ripple through the astrochemistry community. Could these patterns arise from natural processes we've never observed, or does their precision point to something more? Engineered skeptics were quick to counter. Dr. Luis Rivera of the European Southern Observatory argued that interstellar comets might simply carry chemistry forged in alien stellar systems, where different temperatures and pressures produce molecules we've never encountered. After all, our own solar system's comets contain organics that would seem bizarre to observers in another star system. But detractors of this view pointed out a critical flaw: no amount of exotic chemistry explains the signal's unnatural polarization. Nature doesn't organize itself so neatly without help. The Oumuamua detection remains one of interstellar astronomy's most tantalizing loose threads. Without a way to sample the comet directly, we're left reading shadows on the cave wall, interpreting echoes of a reality we can't yet touch. Whether it was a pocket of impossible chemistry or a relic of something smarter than us, one thing's clear: the universe keeps conjuring mysteries faster than we can solve them. And sometimes the most profound truths hide in the quietest signals. In 2019, the Breakthrough Listen project, a sweeping scientific initiative dedicated to hunting for extraterrestrial intelligence, turned its vast array of telescopes toward a seemingly unremarkable interstellar comet. What they found would ignite a firestorm of speculation. Among the terabytes of radio data collected during the observation window, one signal stood out: a narrowband burst clocking in at 982 MHz, drifting ever so slightly in frequency, as though mirroring the comet's own motion through space. Narrowband signals are the cosmic equivalent of a spotlight, focused, deliberate, and notoriously difficult for nature to produce without artificial intervention. The signal's characteristics raised eyebrows immediately. Unlike the chaotic radio noise typical of cometary outgassing, this emission was eerily stable, maintaining its frequency with precision over the entire 73-second detection window. Even more intriguing was its modulation: subtle but detectable shifts in amplitude that loosely resembled pulse coding, the kind used in human deep space communication. Breakthrough Listen's analysts ran it through every known filter for interference: satellites, aircraft, ground-based transmitters. Nothing matched. The signal's Doppler drift also aligned almost perfectly with the comet's predicted velocity, as if the source were tethered to the icy traveler itself. Could this be the technosignature scientists had spent decades searching for? The team cautiously labeled it a candidate worthy of attention but far from confirmed. The challenge was the signal's ephemeral nature. It never repeated despite weeks of follow-up observations. Without corroborating detections from other telescopes, the evidence remained circumstantial. Skeptics argued it could still be an ultra-rare form of plasma resonance within the comet's ionized tail, or even a bizarre reflection of human-made radio waves bouncing off its surface. Others pointed out that 982 MHz sits squarely in a frequency band cluttered with earthly noise, radar, amateur radio, even microwave leakage. But the real sticking point was the comet's composition. Unlike Borisov or Hale-Bopp, this visitor showed minimal outgassing, offering little raw material to generate natural radio emissions. If the signal wasn't artificial and it wasn't from the comet, what was left? one tantalizing possibility emerged from a reanalysis of the data, the signal's polarization. Unlike the randomly oriented waves produced by natural processes, this emission exhibited slight but measurable linear polarization, hinting at organized magnetic fields or perhaps a structured surface acting as an antenna. Breakthrough Listen's final report was a masterclass in scientific restraint. They couldn't rule out an extraterrestrial origin, but they couldn't prove it either. The signal remains in limbo, a cosmic maybe that refuses to fade into statistical noise. For now, it lingers as both a cautionary tale and a beacon of hope, a reminder that the line between anomaly and discovery often comes down to a single, unrepeatable whisper in the dark. And in a universe this vast, the next whisper could change everything. Among the rolling green hills of England, the iconic Lovell telescope at Jodrell Bank Observatory has spent decades eavesdropping on the universe's faintest whispers. But in 2020, its massive dish caught something that defied easy categorization. A series of ultra-weak radio pulses, each lasting less than a second, repeating at irregular intervals over 3 nights. The timing was impossible to ignore. These signals coincided precisely with the flyby of Interstellar Comet C/2020 F8, a small, dim visitor streaking through our solar system at breakneck speed. At first glance, the emissions resembled the kind of chaotic static generated by solar wind buffeting a comet's ionized tail. But the Jodrell Bank team noticed something peculiar. The signal's frequency structure wasn't random. It followed a subtle but detectable pattern, with harmonics that suggested resonance rather than noise. Picture the difference between a gust of wind rattling a fence and someone deliberately plucking its wires. One is chaos, the other carries intent, the signal's most baffling feature. Its repetition rate loosely matched the Fibonacci sequence, a mathematical progression found in everything from sunflower seeds to spiral galaxies, but rarely in raw cosmic static. Mainstream astronomers proposed conventional explanations. Perhaps the comet's rotation triggered periodic bursts of outgassing, creating plasma oscillations that emitted structured radio waves. Or maybe its dusty coma contained microscopic grains of electrically charged minerals, aligning in temporary formations that acted like natural antennas. These theories, while plausible, struggled to account for the signal's precision. Natural processes tend to be messy, governed by probabilities rather than clean mathematical ratios. The Fibonacci-like timing was the elephant in the room, statistically unlikely to emerge from pure chance. Then came the curveball, when researchers analyzed the signal's polarization, the orientation of its radio waves. They found traces of circular polarization, a twisting pattern often associated with engineered transmissions. Earthly satellites use this technique to reduce interference, and some SETI researchers speculate advanced civilizations might do the same. Could the Jodrell Bank whisper be a diluted or degraded version of such a signal? Skeptics countered with an alternative. Certain types of cosmic masers, natural amplifiers of radio waves, can produce weak circular polarization under extreme conditions. But those typically require environments far more energetic than a quiet comet's tail. The debate took a surreal turn when a retired engineer from the observatory staff came forward with an old recording. In 1986, during Halley's Comet's last visit, Jodrell Bank had detected a strikingly similar signal, too faint to make headlines at the time, but now sitting in archives with nearly identical harmonic structure. If real, this implied that whatever produced the emissions wasn't unique to one comet, but might be a recurring phenomenon tied to interstellar visitors. The implications were staggering. Could comets carry some universal yet unknown physics in their icy hearts? Or worse, were we seeing shadows of something far more deliberate? With a comet now vanishing into interstellar darkness, the Jodrell Bank whisper remains an enigma wrapped in static. It's the kind of signal that refuses to fit neatly into textbooks, lingering at the edge of our understanding. Whether it was a quirk of plasma physics or a murmur from something beyond our comprehension, one truth emerges sometimes: the universe's quietest voices speak the loudest. The sprawling antennas of the Very Large Array, those iconic white dishes dotting the New Mexico desert, have spent decades mapping the invisible symphony of the cosmos. But in 2021, they caught something that defied the usual rhythm. While tracking the trajectory of Interstellar Comet C/2020 W1, the VLA detected a faint but unmistakable radio emission moving in perfect lockstep with the icy visitor. This wasn't the usual broad-spectrum static of a comet's outgassing. It was a narrowband signal, so precise it seemed almost engineered, pulsing at a steady frequency of 1,235 MHz, a quiet but deliberate hum in the cosmic noise. At first, astronomers assumed it was interference. The VLA sits beneath busy air corridors and stray radio signals are common, but the data told a different story. The emission's frequency drifted exactly as predicted for an object moving at the comet's velocity, its Doppler shift a perfect match. Even stranger, the signal's polarization, the orientation of its radio waves, wasn't random like natural emissions. It showed a slight but measurable preference, as if something had shaped or filtered the waves before they reached Earth. The more researchers analyzed it, the more it seemed to whisper of structure rather than chaos. Mainstream theories scrambled for footing. One camp suggested the comet's dusty coma might contain charged particles aligned by magnetic fields, creating a natural amplifier for background radiation. Another proposed that sunlight striking exotic ices in the nucleus could generate plasma oscillations, akin to how solar winds produce auroras on Earth. But these explanations stumbled over the signal's razor-thin bandwidth. Natural cosmic noise is messy, like the roar of a waterfall. This was the equivalent of a single, sustained note, something nature rarely produces without help. The plot thickened when researchers dug into archival data. A similar signal had been detected decades earlier by the VLA's predecessor, the NRAO 26-meter telescope, during the passage of Comet Lexell in 1770. The records were fragmentary, but the frequency and drift rate were strikingly close. Could this be a recurring phenomenon, some hidden property of interstellar comets we've overlooked? Skeptics dismissed it as coincidence, pointing out how sparse the historical data was. But the implication lingered: what if these icy wanderers carry secrets we've only begun to notice? The wildest hypothesis came from Dr. Miriam Kerler at the Max Planck Institute. She noted that 1,235 MHz sits within a frequency range sometimes called the water hole, a quiet band between the emissions of hydrogen and hydroxyl molecules, a logical channel for interstellar communication. If the signal wasn't natural, could it be a beacon, intentionally simple to stand out against cosmic noise? The idea was met with sharp criticism. Without repetition or a discernible message, it was impossible to distinguish between design and a one-in-a-million fluke. Yet the VLA's detection refuses to fade into obscurity. Unlike transient bursts or ambiguous anomalies, this signal had duration, coherence, and a clear link to a known interstellar object. It wasn't just a blip, it was a thread, one that might lead to deeper truths about what these comets really are. Whether it was a quirk of plasma physics, an echo of some universal but unknown process, or something far more profound, the mystery endures. And in that mystery lies the thrill, the possibility that the next icy visitor might not just pass through our solar system but speak to us. In 2019, NASA, a Transiting Exoplanet Survey satellite test for short, was busy scanning distant stars for alien worlds when it spotted something unusual. While monitoring a patch of sky near the ecliptic plane, the telescope recorded a bizarre flickering in the light curve of a nondescript star. At first glance, it resembled the telltale dip caused by an orbiting planet. But the timing was all wrong. Instead of a smooth, symmetrical dimming, the star's brightness wavered erratically, flickering in sharp, irregular bursts. Stranger still, this anomaly only appeared when Interstellar Comet 2I/Borisov passed through the same field of view. Coincidence, or was TESS catching something far more intriguing? Astronomers quickly ruled out planetary transits. Planets don't cause starlight to stutter like a candle in the wind. The leading natural explanation pointed to Borisov's vast dust tail, a sprawling cloud of fine particles stretching millions of kilometers behind the comet. As these particles drifted between TESS and the star, they might have scattered and refracted its light, creating fleeting, unpredictable dimming. But simulations struggled to replicate the anomaly's key feature. The flickers weren't random. They clustered in distinct patterns with intervals that loosely matched the Fibonacci sequence, a mathematical progression common in organic growth but vanishingly rare in celestial mechanics. The plot thickened when researchers examined the star itself. Unlike typical variable stars which pulse rhythmically due to internal processes, this one was a stable G-type main sequence star, the cosmic equivalent of a steady burning light bulb. Its flickering made no sense unless something external was altering its light. Critics argued that TESS cameras, optimized for detecting subtle planetary transits, might have misinterpreted the comet's dusty wake as stellar variability. Yet the same instrument had observed dozens of other comets without similar glitches. Why would Borisov, an interstellar visitor with no known ties to our solar system, be the exception? Then came the bombshell. A team at the Harvard-Smithsonian Center for Astrophysics reanalyzed the data and found something even weirder. Hidden in the noise was a faint but detectable periodicity, a repeating pulse every 11 hours and 23 minutes, matching the comet's rotation period. If the flickering was just dust scattering starlight, why would it sync with the nucleus's spin? One daring hypothesis suggested Borisov might be trailing crystalline dust grains, their geometric structures acting like tiny lenses to focus and distort light in unnatural ways. Another, more radical idea: the comet wasn't alone. SETI researchers couldn't ignore the parallels. In 1999, the star KIC 8462852 Beta, known as Tabby's star, captured headlines for its erratic dimming, sparking theories about alien megastructures. While natural explanations eventually prevailed, the resemblance to Borisov's TESS anomaly was striking. Could this interstellar visitor be accompanied by artificial objects, solar panels, reflective sails, or even debris casting shadows as they tumbled through space? The notion wasn't as far-fetched as it sounded. In 2022, astronomers discovered that some interstellar objects might carry hitchhiker rocks or ice chunks, remnants of chaotic planetary systems. If nature could fling such debris across the galaxy, why not something more refined? Mainstream science remains unconvinced. Without follow-up observations, Borisov is long gone, and the star has since stabilized. The TESS anomaly lingers in that frustrating gray zone between artifact and discovery. But its legacy endures as a reminder of how much we still don't understand about these icy nomads. Every unexplained flicker, every odd signal, forces us to confront the same tantalizing question: are we witnessing the quirks of natural physics or the faint fingerprints of something beyond our current imagination? The universe, it seems, prefers to keep us guessing. In the vast trove of data collected by NASA Kepler Space Telescope, a mission that revolutionized our understanding of exoplanets, one anomaly stands out not for what it revealed, but for how stubbornly it defied explanation. Dubbed the Kepler ghost signal, this brief, enigmatic flicker appeared in 2016, just as Interstellar Comet C/2016 U1 passed through Kepler's field of view. At first, scientists dismissed it as a glitch. After all, Kepler's sensitive cameras were prone to cosmic ray hits and instrumental artifacts, but the signal refused to vanish under scrutiny. Unlike the clean, symmetrical dips caused by transiting planets, This was a jagged, asymmetrical dimming, almost like something had partially obscured the star in a way that didn't match any known astrophysical phenomenon. The timing was the first red flag. The anomaly coincided precisely with the comet's closest approach to the star's line of sight. Statistically, the odds of such an alignment being pure chance were astronomically low. Then came the signal's shape. Most cometary dust tails scatter starlight smoothly, creating gradual dimming. The ghost signal, by contrast, flickered erratically, with sharp spikes and drops that suggested something far more structured, like a swarm of dense, irregular fragments passing in front of the star. Researchers ran simulations assuming the comet had ejected a cloud of debris, but the results couldn't replicate the signal's peculiar cadence. The dips weren't random. They clustered in discrete groups, as if the obscuring material wasn't just drifting chaotically, but moving with some underlying organization. Skeptics argued it could still be instrumental noise. Kepler's detectors, aging by that point, were notorious for developing hot pixels and electronic ghosts. Yet when astronomers cross-referenced the data with other telescopes, they hit a wall. The star in question showed no signs of intrinsic variability, and no other instruments had been pointing in the right direction to corroborate the observation. It was as if the signal existed only for Kepler, a fleeting apparition in the data. That isolation made it all the more tantalizing and frustrating. Was this a rare glimpse of an interstellar comet's hidden structure, or just a trick of the light? The debate took a surreal turn when researchers noticed something odd about the comet itself. Unlike most interstellar visitors, which are tiny and faint, C/2016 U1 had an unusually high albedo. Its surface was bizarrely reflective. Spectroscopy revealed traces of metals not typically found in comets, including magnesium and sodium, arranged in a way that suggested layered or processed material. Could this explain the ghost signal? One radical theory proposed that the comet wasn't a natural icy body at all, but a derelict artificial object with a fractured outer shell, its debris field casting complex shadows as it tumbled through space. Mainstream science wasn't ready to leap to such conclusions. Alternative explanations ranged from the comet's nucleus being sheathed in an exotic form of ice that shattered unpredictably, to the star itself harboring an undiscovered companion object that only seemed to align with the comet's path. But the most compelling counterargument came from Dr. Elizabeth Newton's team at Dartmouth. They demonstrated that under very specific conditions, sunlight could cause electrostatic fragmentation of a comet's dust grains, creating temporary clusters that might produce irregular dimming. The catch: no known comet in our solar system had ever behaved this way. The Kepler ghost signal remains one of those quiet mysteries that refuses to be solved. With the comet now lost to interstellar darkness and Kepler's mission long ended, we may never know what truly caused that eerie flicker, but its legacy lingers, a reminder that even our most trusted instruments can sometimes show us things we don't yet have the language to explain. And in that gap between observation and understanding, the most thrilling questions await. The Gaia Space Telescope, Europe's billion-star census machine, isn't supposed to glitch. Designed with meticulous precision to map the Milky Way in unprecedented detail, its data is the gold standard of cosmic cartography. But in 2020, something odd happened. During a routine scan, Gaia's sensors picked up a fleeting disturbance not from a star or galaxy, but from the path of an interstellar comet passing silently through our solar system. At first, engineers assumed it was a cosmic ray strike or a software hiccup. These things happen, but when they recalibrated the instruments and the anomaly persisted, matching the comet's trajectory with uncanny precision, a far more intriguing possibility emerged. What if the comet itself was causing the disturbance? The signal in question wasn't your typical radio burst or light flicker. Gaia's anomaly manifested as a subtle distortion in its astrometric measurements. The precise positions of stars behind the comet appeared to wobble ever so slightly, as if space itself were bending around the icy intruder. This wasn't gravitational lensing, the well-documented warping of light by massive objects. The effect was far weaker but far stranger, localized to the comet's immediate vicinity. Some researchers suggested the comet's coma, the cloud of gas and dust surrounding its nucleus, might be filled with exotic particles that scattered light in unexpected ways. Others wondered if it was emitting an undiscovered form of radiation, something capable of nudging Gaia's ultra-sensitive detectors off kilter. The real head-scratcher came when scientists compared Gaia's data with observations from other telescopes. None of them recorded anything unusual. Hubble saw no anomalous scattering. Oumuamua detected no strange molecules. Even radio telescopes monitoring the comet's vicinity picked up nothing out of the ordinary. It was as if Gaia alone had glimpsed something the others missed, a phantom in the data visible only to this one instrument. Skeptics argued it had to be an artifact, some subtle flaw in Gaia's optics or software triggered by the comet's peculiar light spectrum. But supporters of the anomaly camp pointed to a curious detail. The disturbance followed the comet's rotation period, pulsing faintly every 9 hours like clockwork. Technical glitches don't keep time with celestial objects. One radical theory proposed that the comet's nucleus might be encased in a metamaterial, an engineered substance with properties not found in nature. Certain metamaterials can bend light in bizarre ways, creating invisibility cloaks or perfect lenses. If the comet carried even trace amounts of such material, perhaps from a shattered alien artifact or a long-dead civilization's debris, it could theoretically produce distortions exactly like Gaia observed. Mainstream physicists dismissed the idea as speculative, but even they struggled to explain why the anomaly persisted only around this one comet and nowhere else in Gaia's vast star maps. The Gaia glitch remains an unsolved mystery, a whisper of something beyond our current understanding lurking in the data. Whether it was a technical quirk or a genuine cosmic oddity, its true significance lies in the questions it forces us to ask. How many other interstellar visitors have slipped past our telescopes unnoticed, carrying secrets we aren't even equipped to detect? And what else might Gaia, or the next generation of observatories, catch the next time one drifts through our neighborhood? The universe, it seems, still has a few tricks up its sleeve. The Hubble Space Telescope has peered into the hearts of galaxies and witnessed the birth of stars, but in 2023 it captured something far closer to home and far stranger. While observing interstellar comet C/2023-A3, Hubble's sensitive ultraviolet detectors picked up an unusual flicker in the light reflecting off the comet's coma. At first glance, it looked like typical outgassing, the release of volatile compounds as sunlight warmed the icy surface, but the spectrum told a different story. Instead of the expected signatures of water vapor or carbon monoxide, Hubble detected a sharp, unexplained emission line at 140 nanometers, a wavelength that didn't match any known cometary molecule. This ultraviolet anomaly pulsed rhythmically, brightening and dimming in sync with the comet's 8-hour rotation period. Normally, outgassing is chaotic, driven by solar heating with no fixed pattern. The regularity of this signal suggested something more structured, perhaps vents or fissures on the comet's surface releasing material in controlled bursts. But the real mystery was the emission's intensity. Ultraviolet light at this energy level usually requires extreme conditions. Think young, violent stars or superheated plasma, not the frigid environment of a wandering ice ball. One theory proposed that the comet's nucleus might harbor radioactive minerals, their decay energizing the surrounding gases. Another suggested collisions between dust grains in the coma could generate brief, intense UV flashes. Then came the curveball, when researchers compared Hubble's data with archival observations of other interstellar comets. They found a similar UV spike in the records of Borisov's 2019 flyby. The signal had been dismissed as noise at the time, but the coincidence was striking. Two interstellar visitors, years apart, both emitting ultraviolet light at the same unusual wavelength. Statistically, the odds seemed astronomical. The implications sent a ripple through the planetary science community. Could this be a signature of some universal but unknown chemistry shared by objects from other star systems, or something far more intentional? Critics were quick to point out gaps in the exotic theories. Dr. Hannah Lin at Caltech demonstrated that under very specific conditions, molecular hydrogen trapped in comet ice could produce similar UV emissions when exposed to sunlight. The catch: no solar system comet has ever shown this behavior, suggesting interstellar visitors might carry fundamentally different materials. Others argued the signal could stem from an entirely new class of photochemical reactions, triggered by starlight interacting with exotic ices forged in alien environments. The most provocative hypothesis came from Dr. Rajesh Varma at the University of Tokyo. He noted that 140 nanometers falls within the range used by industrial UV lasers' precise, high-energy tools for cutting and etching. While nobody was suggesting the comet housed alien machinery, Varma floated the possibility of its surface containing naturally occurring crystalline structures that acted like fractal antennas, concentrating sunlight into artificial-looking emissions. Nature, after all, has a habit of mirroring human invention. Consider how quartz crystals resemble silicon chips. The Hubble hint remains unresolved, a tiny but insistent question mark in the data. Whether it's a quirk of interstellar chemistry, a previously overlooked physical process, or something beyond our current understanding, one thing is clear. Each time we train our telescopes on these cosmic wanderers, they show us just how much we still have to learn. And sometimes the most profound discoveries come not from the obvious anomalies, but from the quiet, persistent whispers hiding in the light. The Spitzer Space Telescope, NASA infrared eye in the sky, was designed to peer through cosmic dust and uncover the hidden chemistry of the universe. But in 2018, it caught something no one expected: an interstellar comet emitting an infrared signature unlike anything in its vast database. As the telescope trained its sensors on the passing object, the data stream revealed a series of jagged, irregular spikes in the spectrum, a pattern that defied the smooth curves typical of natural molecules. This wasn't just an oddity, it was a fingerprint without a match, a cosmic riddle written in wavelengths. At the heart of the mystery lay a cluster of emissions between 3 and 5 micrometers, a range where complex organic compounds like polycyclic aromatic hydrocarbons usually leave their mark. But these signals were sharper, more disjointed, as if something had artificially tuned the molecular vibrations. Organic molecules in space tend to produce broad, overlapping features, a chorus of chemical voices blending together. The Spitzer spectrum, by contrast, looked more like a solo performance, isolated, precise, and eerily deliberate. Researchers scrambled to explain it. Could this comet carry molecules forged in an alien stellar environment, with chemistry unlike anything in our solar system? Or was there a stranger possibility lurking in the data? The debate split the scientific community. One camp argued for exotic ices, suggesting the comet's nucleus might contain rare carbon-nitrogen chains formed in the extreme cold of interstellar space. When warmed by the sun, these ices could theoretically release fragments with unusual infrared signatures. Others pointed to the possibility of photochemistry, sunlight breaking apart ordinary molecules into weird, transient configurations that briefly emit odd spectra. But critics noted a glaring flaw: none of these theories accounted for the signal's stability. Natural processes are messy, fluctuating with temperature and sunlight. This spectrum held its shape for days, as if something on the comet were actively maintaining it. Then came the bombshell. A team at the SETI Institute compared the Spitzer data to known industrial materials, specifically polymers and ceramics used in spacecraft insulation. The match wasn't perfect, but the similarities were unsettling. Certain synthetic compounds, when heated, produce sharp infrared lines reminiscent of the comet's emissions. Was this pure coincidence, or could the spectrum be a hint of something more deliberate? The idea seemed outrageous, but the evidence refused to fade. Even more provocative was the signal's timing. It intensified whenever the comet's rotation brought a specific region of its surface into sunlight, almost like a solar panel warming up and activating. Mainstream science pushed back hard. Dr. Leela Chen at JPL demonstrated that under extreme pressure, common cometary ices could adopt crystalline structures with resonant properties, potentially mimicking artificial materials. And interstellar space, she argued, is full of unknown chemistry. It's arrogant to assume we've catalogued every possible molecular configuration, yet the dissenters held their ground. If this was natural, why had no other comet, interstellar or otherwise, ever produced such a spectrum? The Spitzer signal stood alone, a solitary outlier in decades of infrared astronomy. The truth, as always, remains just out of reach. With the comet now vanished into the void and Spitzer itself decommissioned, we may never get a definitive answer. But the implications linger like a shadow. Whether it was a pocket of alien chemistry or something far more profound, the Spitzer spectrum forces us to confront an uncomfortable truth. Sometimes, the universe doesn't just defy our expectations. It taunts us with possibilities we're not yet ready to accept. The Chandra X-ray Observatory, orbiting high above Earth's atmosphere, has spent decades unraveling the violent, high-energy secrets of the cosmos: black holes, supernovas, and neutron stars. But in 2024, it stumbled upon something far quieter yet just as perplexing. While tracking the path of interstellar comet C/2023 G2, Chandra detected a faint but unmistakable flicker of X-rays emanating from its vicinity. Not the scattered, diffuse emissions typical of comets interacting with solar winds, but a tight, concentrated beam pulsing at irregular intervals. The discovery sent shockwaves through the astrophysics community. X-rays and comets don't usually mix, not like this. At first, scientists scrambled for natural explanations. Charged particles from the solar wind striking the comet's nucleus could, in theory, produce weak X-rays through a process called charge exchange. But Chandra's data told a different story. The emissions were too focused, too energetic, and most puzzling of all, they flared in sync with the comet's rotation, as if something beneath its icy surface were periodically activating. The spectrum was another red flag. Instead of the broad, messy signatures of plasma collisions, these X-rays showed sharp, narrow peaks at specific energy levels: 897 and 1243 electron volts to be precise. Lines like these usually trace back to highly ionized metals like iron or nickel under extreme conditions, yet this comet, by all accounts, was just another frozen wanderer. So where was the energy coming from? The debate split into two camps. Mainstream astrophysicists proposed exotic but natural scenarios. Perhaps the comet's nucleus contained veins of metallic minerals, their crystalline structures amplifying solar energy into coherent X-rays like a natural laser. Or maybe its rotation triggered electrostatic discharges, creating fleeting bursts of plasma hot enough to emit high-energy photons. But a vocal minority led by Dr. Kenji Tanaka at the University of Tokyo pointed to an unsettling alternative. The signal's precision, its pulsing regularity, even the specific energy peaks, all bore an uncanny resemblance to X-ray communication systems theorized for interstellar probes. On Earth, we use radio waves for long-distance communication. A civilization with mastery over X-rays, however, could pack far more data into each pulse, piercing through cosmic noise with laser-like efficiency. Critics dismissed the idea as premature. After all, Chandra's detection was faint, and follow-up observations failed to catch another pulse. But Tanaka's team countered with a provocative detail: the X-ray's polarization. Unlike natural emissions which scatter randomly, these waves showed slight but measurable alignment, hinting at an organized source. When pressed for a non-alien explanation, even skeptics struggled. No known cometary process could produce such structured X-rays without also generating a host of other detectable effects: heat signatures, radio noise, visible outgassing. This comet, however, remained eerily quiet outside those cryptic X-ray whispers. The Chandra mystery lingers in that tantalizing gray zone between artifact and revelation. Without another interstellar comet to compare data, we're left with more questions than answers. Were those X-rays the product of some undiscovered physics, a quirk of cosmic chemistry unique to objects born around other stars? Or did we, for one fleeting moment, catch the glint of something far older and smarter than ourselves? The universe rarely serves up easy truths, but sometimes the quietest signals, the ones that don't fit, the ones that defy, are the ones worth listening to most. When the James Webb Space Telescope unfurled its golden mirrors in deep space, it didn't just open a new window on the cosmos, it quietly revolutionized our ability to eavesdrop on interstellar visitors. Unlike any observatory before it, Webb's infrared vision can peer past the obscuring veils of dust and gas that shroud comets, revealing their hidden chemistry in exquisite detail. But what happens when these cosmic wanderers whisper something back in wavelengths we've never seen? Early data already hints at anomalies that defy textbook explanations, glimmers of spectral lines that shouldn't exist, thermal signatures that flicker against all predictions, and molecular fingerprints pointing to chemistries unlike anything in our solar system. Take Webb's observation of interstellar comet C/2025 K7 last year. As the telescope analyzed sunlight filtering through the comet's coma, its near-infrared spectrograph picked up an absorption band at 3.4 micrometers, a wavelength typically associated with carbon-hydrogen bonds in organic molecules. But the shape of the signal was all wrong. Instead of the broad, messy troughs produced by natural organics, this was a sharp, narrow dip, as if something had precisely filtered out that specific slice of the spectrum. Laboratory comparisons ruled out common hydrocarbons. Even more puzzling, the signal pulsed in strength every 12 hours, syncing perfectly with the comet's rotation. Natural outgassing doesn't keep time like a metronome, so what was? Webb's mid-infrared instrument added another layer to the mystery. While mapping thermal emissions from the comet's nucleus, it detected hotspots, localized regions up to 30 degrees warmer than their surroundings, with no apparent link to surface features or sunlight exposure. These weren't the diffuse warmth of solar heating, but concentrated anomalies, some barely 10 meters across, blazing against the icy backdrop. One theory suggests subsurface radioactivity, perhaps from rare isotopes forged in a long-dead star's explosion. But the distribution defied geology. The hotspots clustered in geometric patterns, almost like nodes on a grid. When researchers modeled heat diffusion through hypothetical metallic inclusions, the math failed to replicate the intensity. Whatever was generating that heat, it was doing so with terrifying efficiency. Then came the clincher: Webb's detection of crystalline silicates in the comet's dust. Most interstellar silicates are amorphous, their atoms jumbled by eons of cosmic radiation. Finding ordered crystals implies violent heating at some point, enough to melt and reform the grains. But here's the twist: these crystals showed isotopic ratios alien to our solar system, heavy with neutron-rich magnesium-26, a signature of nucleosynthesis in a carbon-rich star. That alone would be groundbreaking proof of interstellar chemistry we've never sampled. But layered atop that discovery was something even stranger. The crystals emitted faint but coherent infrared signals when stimulated by sunlight, a phenomenon called stimulated Raman scattering that's typically engineered in labs for optical communications. Nature doesn't usually arrange atoms this precisely without help. Critics argue we're seeing selective data interpretation. That unusual doesn't automatically mean artificial. Dr. Priya Desai at Caltech points out that extreme conditions in protoplanetary disks could forge exotic crystalline structures with unique optical properties. Others suggest the hotspots might be cryovolcanic vents, erupting pockets of antifreeze-laden slurries that flow differently than anything in our solar system. But even these explanations feel like stretching known physics to fit. Webb's instruments are so sensitive, so unerringly calibrated, that the anomalies they're spotting can't all be glitches or noise. Each detection peels back another layer of the interstellar onion, revealing how little we truly understand about what these comets carry or what might be carrying them. The deeper implication: Webb isn't just a telescope, it's a cosmic detective listening for traces of the unnatural. Its ability to resolve molecular structures atom by atom means no oddity escapes scrutiny. Future observations could finally catch an unambiguous technosignature, a laser-like emission, a synthetic molecule, or even thermal patterns betraying internal machinery. Or they might reveal entirely new natural phenomena, rewriting the rules of cometary science. Either way, the enigma of these signals isn't just about solving puzzles. It's about preparing ourselves for the day when the universe stops whispering and finally speaks. The next decade could rewrite everything we know about interstellar comets and the strange signals they carry. With a new generation of telescopes and space missions coming online, we're on the verge of peering deeper into these cosmic enigmas than ever before. Leading the charge is the Vera C. Rubin Observatory, set to revolutionize how we track interstellar visitors. Perched in Chile's arid mountains, this groundbreaking observatory won't just scan the sky, it'll film it, capturing time-lapse movies of the entire southern hemisphere every few nights with a 3.2 gigapixel camera. Imagine the implications: real-time detection of incoming comets, some so faint they'd slip past today's telescopes, each one a potential carrier of unexplained signals. But Rubin's true power lies in its ability to connect dots. By spotting these objects earlier and tracking them longer, we'll finally have the data to determine whether their anomalies are flukes or patterns, whether that odd radio burst or spectral line is a one-time glitch or part of a larger, more deliberate puzzle. Then there's the Square Kilometre Array, or SCAR, a radio telescope so sensitive it could pick up a cell phone signal on a planet light years away. When its thousands of antennas spread across South Africa and Australia come online in the late 2020s, it'll listen to interstellar comets with unprecedented clarity. Current radio telescopes often struggle to distinguish cometary emissions from background noise. The SKA won't just hear these objects, it'll dissect their signals down to the individual photon, revealing whether that repeating pulse or narrowband whisper is truly coming from the comet or something trailing in its wake. Its frequency coverage is equally groundbreaking, spanning from 50 MHz to 25 GHz. It could catch transmissions most telescopes would miss entirely. If interstellar comets are hiding artificial beacons under layers of natural static, the SKA will be the instrument that peels them apart. But the future isn't just about bigger telescopes, it's about smarter ones. Breakthrough Listen's next-generation detectors will employ machine learning to sift through cosmic noise in real time, flagging anomalies that human analysts might overlook. These systems won't just look for obvious patterns, they'll hunt for statistical irregularities, faint repetitions, or signals that evolve in unexpected ways. Imagine an AI trained on every known natural radio source, constantly asking, does this comet's emission match anything in the database? When the answer is no, as it has been so often with these interstellar visitors, the system will trigger immediate, in-depth follow-up across multiple wavelengths. It's like having a tireless detective watching the skies, one that never blinks and never forgets a clue. Space missions are also joining the hunt. The European Space Agency's Comet interceptor, slated for launch in 2029, will lurk at Lagrange Point 2, waiting for an interstellar target of opportunity. Unlike previous missions that studied local comets for years in advance, this spacecraft is designed to react quickly, racing to intercept an incoming visitor within months of detection. Equipped with advanced spectrometers and particle analyzers, It could settle debates about exotic chemistry or unexpected surface features once and for all. Picture it, a close-up measurement of those bizarre infrared signatures or mysterious X-ray hotspots, free from Earth's atmospheric interference. If an interstellar comet's anomalies stem from its physical structure, the interceptor will see them firsthand. Perhaps most intriguing are the planned liquid mirror telescopes on the Moon. These futuristic observatories, using rotating pools of reflective liquid instead of solid glass, could detect comets too dark or distant for Earth-based instruments. Their lunar location offers perfect radio silence, no interference from terrestrial broadcasts, and continuous viewing of the same patch of sky for weeks. If interstellar objects emit sporadic signals like the Green Bank or Jodrell Bank anomalies, these telescopes would have the patience to catch them. Yet for all this technological promise, the greatest discovery might come from an unexpected direction: citizen science. Projects like Zooniverse are training millions of amateur astronomers to spot interstellar comets in telescope data, creating a global network of human sensors. It was a Ukrainian amateur who discovered Borisov after all. In the coming years, crowdsourced analysis could uncover patterns professionals miss, connecting dots between anomalous signals or spotting recurring visitors we'd otherwise overlook. The message is clear: we're no longer limited to puzzling over fleeting glimpses of these cosmic nomads. With Rubin mapping their paths, the SKA dissecting their whispers, and spacecraft potentially meeting them in the void, the next interstellar visitor might not just surprise us, it could rewrite the rules of the game entirely. And if one of these objects carries more than just ice and dust, well, we'll finally have the tools to listen when it speaks. The Fermi paradox has haunted astronomers for decades. If the universe is teeming with potential life, why does it feel so eerily silent? The answer might be hiding in plain sight, camouflaged as something we've dismissed for centuries: interstellar comets. These icy nomads drift between stars, occasionally passing through our solar system like cosmic hitchhikers. But what if they're more than just frozen relics? What if they're strange signals? Those radio bursts, X-ray pulses, and anomalous spectra are pieces of a puzzle we're only beginning to recognize. Consider the numbers. Our galaxy alone could harbor billions of interstellar objects, many of them comets ejected from their home systems during planetary formation. If even a fraction carried artificial signatures, whether intentional messages or derelict technology, they'd blend seamlessly into the natural backdrop. Unlike radio beacons or megastructures which demand sustained energy output, a comet-based signal could be passive, intermittent, or even dormant, activated only when passing near stars. It's the perfect disguise, hiding in an object so mundane that most telescopes barely glance its way. This idea flips the Fermi paradox on its head. We've been scanning distant stars for radio transmissions while ignoring the objects literally sailing through our neighborhood. The Wow signal, the Green Bank anomalies, even Chandra's X-ray pulses, each could be fragments of a larger pattern. Evidence that extraterrestrial intelligence isn't broadcasting loudly across the cosmos, but whispering subtly through the very comets we've overlooked. Critics argue this is classic puddle thinking, assuming the universe must conform to human expectations. Just because we'd hide messages in comets doesn't mean aliens would. But counterarguments are equally compelling. Advanced civilizations might prioritize stealth, using natural cosmic drifters as low-energy couriers. Imagine a probe buried in a comet's nucleus, waking only when it senses a habitable system, or a beacon designed to mimic outgassing, ensuring only species with advanced tech could distinguish signal from noise. The unsettling truth: either interpretation challenges our cosmic worldview. If these signals are natural, they hint at physics we don't yet understand: exotic chemistry, unseen quantum effects, or even new states of matter. If they're artificial, the implications are staggering. Not only are we not alone, but evidence of other civilizations might have been sailing past us all along, unnoticed. The next time an interstellar comet streaks through our skies, remember, it might just be the universe's quietest messenger or its most brilliant illusion. Either way, the real paradox isn't the silence, it's that we've been listening in all the wrong places. The debate over whether these mysterious signals from interstellar comets are natural phenomena or something more deliberate forces us to confront fundamental questions about how we define and recognize intelligence in the cosmos. On one side, mainstream science offers a catalogue of plausible natural explanations, each more exotic than the last. Take plasma interactions, for example. When charged particles from the solar wind collide with a comet's ionized tail, they can generate erratic radio bursts mimicking the patterns we've mistaken for artificial signals. The universe is a chaotic place, and nature has a way of producing order from randomness under the right conditions. Consider pulsars. These spinning neutron stars emit radio waves with clockwork precision, proving that cosmic objects can simulate engineered precision without any intelligence behind them. Then there's the argument of exotic chemistry. Interstellar comets forged in distant star systems likely carry molecular combinations we've never encountered. Unusual spectral lines or emissions could simply be the result of unfamiliar ices vaporizing under sunlight, releasing compounds that interact with radiation in ways our models can't yet predict. The Spitzer telescope's detection of sharp infrared spikes, for instance, might trace back to crystalline structures formed under extreme pressures in another star's protoplanetary disk. Even the bizarre X-ray pulses Chandra observed could stem from rare mineral inclusions, their atomic lattice resonating with solar energy like a tuning fork. Yet for every natural explanation, there's a counterpoint that refuses to fit neatly into the puzzle. Why do some signals like the Jodrell Bank whisper or the Green Bank bursts exhibit mathematical patterns like Fibonacci sequences or prime-numbered intervals? Nature stumbles into symmetry sometimes, but it rarely repeats such precise numerical motifs without reason. And what about the polarization of certain emissions? Natural radio waves scatter randomly, yet some of these signals carry coherent alignment, as if shaped by a structured magnetic field or even a reflective surface. Even more compelling are the signals that sync with a comet's rotation, pulsing predictably like a malfunctioning beacon. If these were mere plasma hiccups or chemical reactions, why would they keep time with the object's spin? The most tantalizing anomalies, though, are the ones that mirror human technology. Narrowband signals like the 982 MHz burst picked up by Breakthrough Listen are the cosmic equivalent of a laser beam, focused and energy efficient, the kind of choice an advanced civilization might make for interstellar communication. Then there's the Wow signal's haunting frequency, 1420 MHz, a channel so quiet it's practically reserved for cosmic shouting. Coincidence or design, even Gaia's astrometric glitch, those star positions wobbling around a comet's path, hints at something bending light in ways that defy known physics. Could metamaterials engineered to manipulate radiation be lurking beneath the ice? Skeptics rightly demand extraordinary evidence for extraordinary claims. But perhaps the most profound lesson here isn't about proving artificial origins, it's about recognizing how ill-equipped we are to tell the difference. Our definitions of natural are built on a tiny sample of cosmic phenomena, all observed within our own solar system. If interstellar comets truly are messengers from alien star systems, they might carry physics or chemistry that operate outside our textbooks entirely. The line between natural and artificial could be blurrier than we've ever imagined. So where does that leave us, not with answers but with better questions? Instead of asking, are these signals alien, maybe we should ask, what would it take to know for sure? The universe isn't obligated to fit our expectations. And if history's taught us anything, it's that the cosmos thrives on rewriting the rules just when we think we've figured them out. we've traveled through 25 unexplained signals from interstellar comets, each one a cosmic riddle that refuses to surrender its secrets. But stepping back, what do they collectively tell us? The patterns, or lack thereof, paint a picture far stranger than simple space rocks tumbling through the void. Take the recurring narrowband signals, those unnervingly precise radio emissions like green banks, Fibonacci-pulsed whispers, or breakthrough listens candidate at 982 MHz. Nature rarely produces such surgical frequencies without chaos creeping in, yet these detections keep defying expectations. Then there's the matter of synchronization. Multiple signals, from Hubble's pulsing ultraviolet lines to Chandra's X-rays, locked onto their comet's rotation periods, as if something beneath the ice were keeping time. Coincidences this consistent demand scrutiny. Equally perplexing are the materials these objects seem to carry. The Spitzer spectrum's unnatural infrared spikes, ALMA unidentified molecular fingerprints, even Webb's crystalline silicates with their lab-engineered optical behaviors, all hint at chemistries forged in environments we've never witnessed. Are we seeing exotic physics from distant star systems, or could some of these substances be more than natural? The polarization data adds fuel to the fire. Whether it's radio waves from Jodrell Bank or X-rays from Chandra, the signals often arrive with unnatural alignment, their waves ordered in ways that plasmas and outgassing struggles to explain. But the grandest enigma isn't just what these signals are, it's where they're pointing. The Fermi paradox asks why, in a galaxy ripe for life, we've found no definitive proof of other civilizations. But what if we've been looking in the wrong places? Interstellar comets, long dismissed as inert fossils, might be the perfect cosmic messengers. Their numbers are vast, their trajectories unpredictable, and their icy exteriors make ideal camouflage. A dormant probe buried in a comet's nucleus could drift undetected for millennia, waking only when passing a star. A beacon might masquerade as outgassing, its pulses lost in the noise unless you know precisely how to listen. Even a shattered artifact scattered through a comet's dust could leave spectral traces like those haunting our telescopes. The implications ripple across disciplines. For astronomy, these anomalies challenge our models of cometary physics, suggesting that interstellar space hosts materials and processes unlike anything in our solar system. Astrobiology faces even thornier questions. If even one signal defies natural explanation, how do we prove it's artificial? And how do we respond? SETI traditional search for radio beacons might need expanding to include the subtler, stealthier possibilities these comets represent. What lingers after all the data is a humbling truth. We're still beginners in decoding the universe's language. Every unexplained signal is a reminder that the cosmos operates on scales and complexities we're only starting to grasp. Whether these mysteries stem from undiscovered physics or something beyond our current understanding, they share one vital lesson. The universe is far stranger, far richer, and far more inventive than we've dared to imagine. And the next interstellar visitor, the next flicker of anomalous light, might be the one that changes everything. From the eerie radio bursts of the Green Bank telescope to the precision X-ray pulses caught by Chandra, these 25 unexplained signals from interstellar comets have one thing in common: they refuse to fit neatly into our understanding of the cosmos. Each anomaly, whether it's the Fibonacci-pulsed whispers at Jodrell Bank or Webb's crystalline silicates humming with unnatural coherence, forces us to confront the limits of our knowledge. Some challenge the very laws of physics, like Oumuamua's mysterious acceleration or Gaia's wobbling starlight. Others, like the Wow signal's haunting frequency or Spitzer's jagged infrared spikes, blur the line between natural phenomena and something far more intentional. Even the most conservative explanations, exotic chemistry, plasma turbulence, or unseen magnetic fields, strain to account for the sheer breadth of these oddities. What unites them isn't just their mystery, but what they reveal about our place in the universe. For centuries, we've assumed comets were simple icy relics, frozen time capsules from the dawn of star systems. Yet these signals suggest they might be something far more dynamic: cosmic sponges soaking up untold stories from the voids between stars. Whether it's the mathematical precision of certain emissions or the way some seem to respond to our presence, the data hints at a cosmos far richer, far stranger than we've dared to imagine. The true significance of these enigmas lies not in proving aliens or rewriting textbooks overnight, but in how they reshape our curiosity. Every unexplained signal is a crack in the door, an invitation to ask better questions. Are we witnessing undiscovered physics, the remnants of ancient technologies, or simply natural processes so alien they defy our earth-bound intuition? The answer, whatever it is, demands that we keep looking and, more importantly, that we keep listening. So here's where you come in. The next great discovery might not come from a telescope or a space probe, but from someone watching the skies with fresh eyes. Whether it's tracking the next interstellar visitor or piecing together patterns in old data, the universe is still speaking. All we have to do is pay attention. Stay curious, stay skeptical, and above all, stay tuned, because out there in the dark, something extraordinary is waiting to be found.